Calculated inflow provides the sum of all inflows into a reservoir, including gauged inflows and ungauged inflows. Gauged inflows are measured at river gauges built on major rivers. A map of Roosevelt Lake shows gauged inflows at Tonto Creek and at the Salt River. Every other water flow in the Roosevelt Lake watershed is an ungauged inflow. Calculated inflows are determined based on two variables, spillway flow and reservoir elevation, which are recorded over a period of time. Using the knowledge of spillway flow and the change in lake elevation over time, we can calculate the total inflow into the lake. This calculation is made without the use of any gauged inflow data. Calculating inflows starts with looking at a reservoir which has a constant elevation through time and a known spillway flow. In this example, the lake elevation is not changing. You can see that the calculated inflow must be equal to the spillway outflow. Spillway outflow is a known quantity, and so the unknown inflow becomes known and is equal to the spillway outflow. When the spillway is flowing and the lake remains at a constant elevation, the unknown inflow can be determined as equal to the spillway outflow. Calculating inflows relies on working knowledge of net area contents tables. The volume of any lake is available in the reservoir net area contents tables for that reservoir. At each lake elevation, this table provides the corresponding area and volume of the reservoir. The volume of the reservoir is typically listed in units of acre-feet at each 1/100th of a foot of lake elevation. Now let's determine how a changing lake elevation over time can be used to determine the unknown inflow. The spillway gates have been closed and the lake rises 1 foot over a period of 1 hour. When a lake elevation has changed over a period of time, the volume in the lake at the lower elevation can be subtracted from the volume in the lake at the higher elevation. This gives the net change in the reservoir volume. This change in reservoir volume over time in units of acre-feet per hour can be converted into units of cubic feet per second. We have shown that a changing lake elevation can be used to calculate the unknown inflow into the lake. With the spillway gates closed, the inflow will increase the water level in the reservoir over a period of time. The volume of water which was added to the lake during that time can then be converted into a calculated inflow in units of cubic feet per second, or CFS. If a spillway is releasing 20,000 CFS and the lake rises 1 foot in 1 hour, what is the unknown inflow? Both of the variables, the spillway release and the lake volume change, will be used to determine the unknown inflow. The spillway release in CFS will be added to the inflow represented by the change in lake volume over time to obtain the unknown inflow. Both of these indicators of inflow can be added together when they occur at the same time. This lake is rising 1 foot while the spillway flow is 20,000 CFS. The unknown inflow is 20,000 CFS, which accounts for the spillway discharge, added to 11,495 CFS, which accounts for the lake volume increase. The unknown inflow has now become the calculated inflow and is 31,495 CFS. When the spillway is flowing and the lake is rising, the unknown inflow is equal to the spillway outflow plus the flow determined from the volume change in the lake. When the reservoir is falling with the spillway gates open, you can see that the spillway flow must be greater than the unknown inflow. To calculate the unknown inflow in this case, start with the spillway flow and then subtract the flow represented by the volume change in the lake over time. If a spillway flow is 20,000 CFS and the lake falls 1 foot in 1 hour, what is the unknown inflow? The inflow represented by the change in lake elevation over time will be subtracted from the inflow represented by the flow through the spillway. The unknown inflow is 20,000 CFS, which accounts for the spillway discharge, minus 11,495 CFS, which accounts for the lake volume decrease. The unknown inflow has now become the calculated inflow and is 8,505 CFS. When the spillway is flowing and the lake is falling, the unknown inflow is equal to the spillway outflow minus the flow determined from the volume change in the lake. Understanding calculated inflows provides a foundation for understanding flood operations at dams. Several examples reinforce the significance of calculated inflows. Number 1, hydrograph and other data is more meaningful to a person who understands that calculated inflow includes both gauged and ungauged inflow. This 1980 hydrograph shows gauged and calculated inflows. Can you identify the ungauged inflows, which are not labeled on this chart? Number 2, understanding calculated inflow provides an intuitive grasp of the meaning of changing lake elevations as large spillway outflows are occurring during a flood. This intuitive feel helps in understanding the WEROC reservoir chart trends and prioritizing action among reservoirs. Number 3, calculated inflow provides information when gauged inflows are unavailable after a communications or data failure or gauging station failure during a flood emergency. Calculated inflow provides information available to a dam tender during a total communications or data failure, or when spillway operational priorities leave no time to communicate with WEROC. The dam tender is trained to track lake elevations and spillway releases manually and to use these to determine calculated inflows once per hour. Understanding this information, the dam tender is in a position to manage the reservoir independently when required. During some emergency operations, the dam tender may not have time for any calculations, yet this understanding of calculated inflow leads to operational principles which can be applied to manage the spillway and reservoir during a flood. In the absence of communications, or when there is no time to communicate with WEROC, the dam tender will operate by using the following 5 principles. These principles may also provide a useful guide for WEROC operations during the peak inflow hours of extreme flood events. Number 1, never let water overtop a spillway gate. Number 2, pick a target elevation, usually 4 or 5 feet from full lake, that is desired at the end of the flood event. Number 3, if the water surface in the lake is rising toward the target elevation, increase the spillway gate opening until the lake stops rising. Number 4, if the water surface of the lake is going down, away from the target elevation, decrease the spillway gate opening until the lake stops falling. Number 5, continue to attempt communications with WEROC when possible.